In this lecture, we are going to talk about the derivative and integral of natural log functions and natural exponential functions. So first, the natural log function. Remember that the natural log function was defined as ln x equals from 1 to x 1 over t dt, and here we want x greater than 0. So we already talked about all these properties in the previous class. Ln of 1 equals 0 because when you have 1 you have upper and lower bound, the same thing, so it gives you 0. The integral gives you 0. And then if you look at the graph, as x goes to infinity, when your x goes to infinity, you are following the graph this way. As x increases, y increases too, and it doesn't really have a horizontal asymptote, so it goes all the way up to infinity. But on the other hand, when x approaches 0 from the positive side, x has to be greater than 0, so when x approaches 0 from the positive side, your y-coordinate gets lower and lower and lower. So when x approaches 0 from the positive side, the y-coordinate, or ln of x, goes to negative infinity. Then we still have this nice logarithmic properties. Log of a product equals the sum of the logs, and log of a quotient is the difference of the logs, and the log of a power, you can pull the exponent to the front. These all holds. And also because ln x is defined as the integral, when you take derivative, you go back to the integrand. So the derivative of ln x is 1 over x. But here, what I want you to observe is that when your x is negative, and we put absolute value here, okay, because when x is positive, ln x is absolute value, so we don't need to worry about that. When x is negative, we still can say, taking ln of the absolute value of x, which will be ln of negative x, because as x less than 0, the absolute value of x equals negative x. Then we use the chain rule. This is my u. The derivative of ln is reciprocal, so 1 over u, which is negative x. As definition, then the chain rule du dx, which is the derivative of negative x. This gives me negative 1. So I'm really having 1 over negative x coming from the reciprocal 1 over x, the derivative, and then times the chain rule give you negative 1. Then the two negative signs cancel each other, you still get 1 over x. So this is what you get. X greater than 0, the derivative of ln, absolute value of x, is 1 over x. When x is less than 0, the derivative of the same expression, ln of absolute value of x, is still equal to x. Hence, we have this. The derivative of ln of absolute value of x equals x. This is true for both positive and negative x's. And then, when the antiderivative of 1 over x will go backward. So the antiderivative of 1 over x is ln of absolute value of x plus c. This completes our picture of power rule. Because in general, we have the integral of x to the nth power dx equals 1 over n plus 1 x n plus 1 plus c. And here, n is not negative 1. And when n equals negative 1, we have this. Okay? N equals negative 1, by the way. X to negative 1 is 1 over x. So that completes our picture of the power rules for integral. Now let's see some example differentiate. The first example, y equals ln x squared plus sine x. So this whole parenthesis is my u. Then dy dx will be ln of u. Taking derivative is 1 over u. So 1 over x squared plus sine x times x squared plus sine x derivative. So this gives me the 1 over the reciprocal of the input of ln times x squared gives me 2x taking derivative, and sine x gives me cosine x taking derivative. So this is 2x plus cosine x over x squared plus sine x. Now second example, when y equals ln of a quotient, we can first use the property of the ln. This will be ln x squared plus 2. ln, or in general log, of a quotient is the difference of the logs. Minus ln x minus 1 to 1/2. This is ln x squared plus 1 minus 1/2. Let me pull the 1/2 to the front. Now I'm going to I prepared my function to a much nicer sort of linear form of ln's. Now I take derivative. So when I take derivative again, each of the input is like a u. So when I take derivative, first of all, I get the reciprocal of the input of ln followed by x squared plus 1, the derivative of the input. So similarly here, I will have x minus 1 as denominator over 1 times x minus 1 derivative. Okay, so I can just put the second part of the chain rule as you are going to multiply by it, right? So you can put it on the numerator, since the numerator for derivative of ln is 1 over x. This gives me 2x over x squared plus 1 minus 2 times x minus 1 for denominator, and numerator is 1. Oh, I'm sorry, this is 2. Yeah, it's 2 everywhere. Also here. It doesn't really change the derivative and anything, but yeah, the denominator should be 2. Sorry about that. Because the ln function can easily turn product and quotient and the powers into sort of linear form of the basic factors, we can use ln function to make our differentiating, huge product and quotient much easier. And this is how you're going to do it. 3 steps. First, you're going to write the function. If it's a function notation, you're going to write it as y. You need to get rid of the function notation and give the output a name. So I didn't do anything but called it y. And also I rewrite my square root as half power, so that I'm going to take natural log on both hand sides. So ln y equals ln of this whole thing. I don't really need the parentheses, but let me copy it. In the future, probably I won't copy the whole thing anymore. Maybe the first time I should. So ln y equals is this one plus this one minus this one with ln everywhere. So it's ln x plus 1 to the third power plus ln sine x to the second power minus ln x squared plus 1 to 1/2. Then I pull the coefficients to the front, plus 2 ln sine x minus 1/2 ln x squared plus 1. Now I'm going to differentiate both hand sides. Y is a function of x, so when you differentiate the left hand side, you get a chain rule. This is 1 over y times y prime. Well, let me say dy dx. On the right hand side, you just do what we have done in the previous two questions. You take the coefficient, each of the inputs is like your u. So I put the input of ln in the denominator and then followed by its derivative on the numerator. 2 sine x on the denominator, derivative of sine x on the numerator, minus 1/2 x squared plus 1 on the denominator, its derivative on the numerator. This gives me 3 over x plus 1 plus 2 cosine x over sine x minus 1/2 times 2x over x squared plus 1. So they got cancelled. Oh, sorry, I missed my x. Finally, I'm going to multiply the y on both hand sides. Let me give this back. So I'm getting dy dx equals y times 3 over x plus 1 plus, well, you can say 2 cotangent x. I don't want to change it. I'll leave it sine and cosine. I think that's okay. Minus x over x squared plus 1. And y is the huge thing we started with. Let's give this back. Square root of x squared plus 1. This is the y that we had, or here, the y that we had. Okay, same thing. Then you copy the whole factor. I hope I can fit it. 2 cos, no I can't. Sine x, I'll do the minus here, minus x over x squared plus 1, closing the parentheses. Okay, so the point here is when you are doing the huge, you are looking for the derivative of a huge product and quotient of some kind of powers, instead of doing a lot of power rule and quotient rule and product rule, use ln function. It sort of pull out all the coefficients and also separate the factors. Okay, now you can try practice number 1 through number 3. Now, next example, we are going to find the integrals. And the formula we rely on is the integral of 1 over x dx is ln absolute value of x plus c. So for the first question, well, again, what we have for 1 over x is that we complete the whole power rule for x. So any power of x, we now know how to find its integral. Here, I'm still going to write it as write the integrand like a polynomial, like 1, 4. This is 3 over x plus 1 dx, where the 3 over x becomes 3 times 1 over x, ln absolute value x plus 1 gives you x, right? That goes there, that goes here. And I'm evaluating from 1 to 4. Since my x sits between 1 to 4, absolute value x is just x itself. So we just have 3 ln x plus x evaluated from 1 to 4. So plug in 4, then plug in 1, where ln 1 equals 0. This is 3 ln 4 plus 4 minus 0 minus 1. I don't need a 0, and I'm getting 3 ln 4 plus 3. Next example, I'm having the integral of ln x over x. So I hope you can sort of observe here 1 over x dx is linked to the derivative of ln x. Actually, it is the derivative of ln x. So I'm going to call my ln x u. So that my du dx will be 1 over x, and multiply dx on both sides. The u is 1 over x dx. Since I'm having definite integral, I need to change the limit as well. X equals 1 goes to u equals ln 1, that's 0. X equals e goes to u equals ln e, and that is 1. Then my integral becomes from 1 becoming 0, e becoming 1. ln x is the u, and 1 over x dx is the du. So I'm just having u to the first power. I add the exponent by 1, I flip it, and I evaluate. This is 1/2 1 squared minus 1/2 0 squared, which is 1/2 times 1, 1/2. Okay, now you can try practice number 4 and number 5. Now we're going to talk about the natural exponential function, which are the exponential functions with base e. We define the natural exponential function as the inverse function of the logarithmic function that we already have. Then I'm not going to show these, but all the rules that you knew are still true based on this new definition where ln x is the integral from 1 to x, okay, 1 over t dt. And then the exponential function, instead of saying it's the power of e, where e is an irrational number, because the thing is, which irrational number we are talking about, right? So this is the precise definition. We start from the integral and then we go back, find our exponential function. Whichever number that makes them corresponding to each other, that's our pick. So since there are inverse functions, exponential composed with logarithmic or logarithmic composed with exponential both give you identities. This is true because f composed with, well, let me not use the circle, f inverse of x equals x. No matter you take ln natural log function as f or the exponential function as f. Also, you can compose it the other way around. The graph of the exponential function looks exactly the same as you knew. When x goes to negative infinity, our y coordinates gets lower and lower but remains above x-axis. So it's approaching at 0, actually from the positive side. It never really reached 0 or go to the negative side. On the other hand, when your x gets bigger and bigger, when x approaches positive infinity, this graph actually rises very fast. The y coordinate also goes to infinity, but in actually faster speed. Then again, all these power rules, remains. When you have addition on exponent, it becomes a product of two powers. And when you have a difference on the exponent, it becomes the quotient of two powers. And when you have power of power, it becomes the product. So on the exponent, they're all the same. And I don't think I want to show you this, but actually the derivative of ex is still ex, which bring us back to the exponential, to the integral. The integral of the ex, e to the x, will remain e to the x with a constant c. Our next example, differentiate y equals e to the x squared. Here's the thing, when you have a chain of exponents, it's going, you read it from top to bottom. So x squared first, then e to the whatever power, which is x squared, okay? So this is really e to the x squared power. It's not this, okay? So exponent, you take the most top one first, the most top ones first. Then, well, apparently it's another chain rule. dy dx will be, this is my u, will be e to the x, taking derivative itself. So, oops, e to x squared will remain the same, but because where x supposed to be in the formula, where's my formula? Where x supposed to be in the formula is not really an x, chain rule tells me I need to take derivative of what takes the place of x in the formula. And that is x squared in this question. So I'm having e to the x squared power times 2x. I want to write my smaller or simpler factors before the huge one. So 2x times e to the x squared power. You don't really need to write the dot, but attachment give you multiplication. Last example for today, we are looking for the integral of sine x e to cosine x power dx. Although it's a very complicated expression, I hope it's clear to you that you will have to call the exponent your u, because e to the x is the only thing you know. So my u will be cosine x, and that means my du dx is negative sine x dx. And here they are, the negative sine x dx. So I have sine x dx, which will be, oh sorry, I don't have the dx yet. So I have du dx equals negative sine x, which means du equals negative sine x dx, which is here. And I don't have the negative sign, so I will give it to du. Sine x dx is negative du. So the integral will be e to the cosine x u sine x dx, which is negative du. This is negative eu du. And the integral of eu is itself. So that's still negative e to the u's power plus c. And I'll give u back. U is cosine x plus c. That's the integral. Now you can finish the packet.